Today we're going to see the constitutive laws and the different representations of, of elements in nature that allows us to model just about any system. What you see on the screen is a chart that is indicative of the kind of elements that we need to look, and I put in here the names of it. As you can see, you have two sources in here. You have two connecting elements. The source elements that we'll use, we will call them SC and SF, meaning source of effort. We already saw what the concept is of generalizing the variables. When I say effort, it could be a force, a torque, a pressure, or a voltage. But when I say source of flow, it could be a source of velocity, of current, of volume flow rate, or of angular velocity. The connections of zeros and one, there's no meaning in the sense of numbers. You know, the zero is a zero. That's not the way we read it here. A zero connection or zero junction is an element that allows us to connect things in different ways. That's why it's called is either a junction for common flow or it is a junction for common effort junction. So what we have in here is that you you have the two connections, two sources, and we have these five other elements. The first element is called an I element, which is the element that allowed us to store kinetic energy. The second element is the C element that allows us to store potential energy. Or we have this R element that allows us to dissipate energy. So you see the three elements, the I, C, and the R, have very unique and distinct functions on a system. I elements store kinetic energy, C elements store potential energy, R elements dissipate energy. And each one acting as a system becomes an important thing. So in here you have the TF element and GY element. These two elements are conservative elements that are designed to help you represent parts of systems that actually conserve energy. They only transform, like for example, a set of gears is a good example. Just transforms one rotation into another. The master cylinder on the brakes on your car is also a conservative element. It's one of these transformers. The only thing it does is transforms mechanical power and motion into hydraulic one. But no energy lost, no energy stored on the element. It's just transformed. And then we need one more element, this GY element, which stands for a gyrator. Gyrator is also called like a cross transformer because it is another conservative element, no dissipation of energy, no nothing like that. It conserves energy, it transforms energy, but the only difference between the transformer and the gyrator is that in the case of the gyrator, the variables are crossed. That's why it's called also cross transformer. What do I mean with this? In an electric motor, for example, the voltage is related to how fast the motor turns. The more voltage, the faster it goes. If you may go for a moment to your childhood, if you have one of those little trains or like a remote control, yeah, you have those trains that go around, and you turn this pot, and the more you turn, the faster it went. You see, in an electric motor, the voltage is directly related to the current. But you see, a voltage is an effort variable, and the current is a flow variable. So instead of relating like flow to flow or effort to effort, like on a gear set you relate one angular velocity to another. Gearbox, like the one in your car, that's exactly what it does. It converts the revolutions of the engine into another speed for the car. But in the gyrator is different because the variables are crossed. One effort, which is voltage, is related to the flow on the other side. So that's the only difference between those two. Okay, let's begin with some symbols also that we're going to need to indicate the connections and the interaction between elements. Like in this case, if you have in moment, you see you have element A and then you have element B. Well, it turns out that this line that we draw from A to B, the line from A to B, indicates the power flow. Power flows from A to B. We did something in here. Yeah, here we go. Sorry, we got a little mess up in there. But in here, we have this, yeah, there we go. We have this ability to write from A to B or from B to A. See? We add another mark. Instead of just having the power flow, we add this mark, this crossbar. And the way I see it here is the way you interpret this. This is as if you were to hold it as a little piston and then you can push it to the side. Let me see if we can actually draw this. Okay. Hold on for a second. Yeah, in here we're gonna go on. I'm trying to make an annotation here, and the system is not cooperating with me. So bear for a second in here. Okay. we'll fix this. There we go. Okay, let's try to write down what I was trying to say. So in here, this is as if we let's see, let's put a pen. Because the slide is dark, we actually need a light pen. So let's try that. See, if I were to hold it with my hand over here, let's just put it here like this. And isn't it true that if I push it this way, as if I'm holding it, you can see that you can say A pushes on B. So that means that the effort goes from A to B. See, the effort goes from A to B. If you do it the other way in here, let's say you're holding it like that, and you push in the direction of the little piston like it. It means that B pushes on A. So effort in this case is going from B to A. That's what it means. So you have the ability to express the power flow by just the half arrow, and the ability to express how the effort goes by the crossbar. See, this is the effort right here. In one case from left to right, and the other one from right to left. That's how we interpret this.
How does it change it if that angle line were to be on A in the last portion where B is putting up the line?
Do you mean in the vertical direction or so?
The one that's angled, the power line.
Yeah.
You would change the power line on that one so it represented the left-hand side on the bottom line. See how it goes from A to B and it has the
If I
slash
change
line?
this angle right here,
Yeah. If you did that on the other side and put it from that, I'm not seeing what the difference is with that slash line.
very good question, because there's no difference. In other words, what you see here,
So you can put the slash
you
line.
see here, let's just draw it here. Huh? The power goes from A to B, but when it comes down to the applying the effort like this, when you read it like this, it's saying that the effort goes from B to A. Okay, so because the crossbar is the indication of the effort. Okay, that's what it means. So you could have one that is like this, but also you could have one that is like that. See?
Can you give us an example of the time when the effort is not on the same side as the power transformation?
Like for
Like the resistive element in the
yeah, like for example, if you have in the in here you have, let's say, let's just put the resistive element in. Here's a good example. This R, you have obviously from here to here You have a voltage and you write voltage equals to I times R, right? So when you have the R element in here and you say, okay, this is my connection to the R element, this equation right here controls where that crossbar goes. Because isn't it true that says that V is the output of R? So that for sure is like that, see? It's as like, remember what I told you about holding it with your hand and pushing it this way. Okay, so that's how we read this symbol. But we need other symbols to do our job. Like here, see? We need this connection, the one that indicates this kind of connection, and we need a zero which indicates this kind of connection. I would just go ahead and state that this one junction is the common flow junction and the zero junction is the common effort junction. So we could just, if we could just write it down, and let's see, we go over here. This one right here would be the common flow junction. And this one, the zero, would be the common effort junction. See? Okay, so those are the ones. Now, the resistive element. The constitutive law is the effort is R times F, and if it is not a linear, you still have the concept because R could change. In fact, the changing R is what it would change many systems. But in looking at the specific constitutive laws of the R element, you see on the slide in front of you, the red crossbar indicates the effort, the way the output goes. So depending on how that effort goes, depending on how it goes, you can see that it's on the side, yeah. And here's the effort, and this is the flow. For this other one, you see also that the effort is on the side, so it goes from the system towards this element. But you see, this does two things. This is saying that the output of the resistive element is E times I, or R times F. In this case, voltage is IR. Just like this, is the effort is equal to the current, here the resistor times the current. But this other one, you see, this says the opposite. It says the output of R is this flow. So what we're seeing here is that the red line indicates the efforts, the green light indicates the flow. So if you have it this way, the equation is different. This is in terms of the output is F is 1 over R times Z. So my point is this. that depending on how we have it written this way or this way, the equation of that element would have to be different. Like in the case on the left hand side, the output is the effort, so you say E is R times F. But in this case, the flow is the input, and flow is 1 over R times E. Okay? This kind of relationship can be plotted into a block diagram. This is what I was saying. I think we need to represent it in the block diagram way, the bond graph way, and the graphical way. So in here, if you have the equation like you're seeing here, 1 over R, E times 1 over R is equal to F, you will have this way. But this one, where you have R, you have the flow times R is equal to E, or E divided by 1 over R is F. So you end up having this element like this, or this element, depending on which one is in your system. So that way we see how in the case of a capacitive element, the C for capacitor, this one is a very important one because you see is the one that deals with integration and derivation. There's two elements like this, the I's, and then there is this C element, okay? So those are two elements that I highly recommend you take the most care of it, because you, depending on whether it is like on the left hand side or if it is like the one on the right hand side, that determines the equations. So you have integral form, which means 1 over c the integral of f dt, and then you have the q dt is equals to f. So that's the differential equation that is born out of this. But you see here, the flow is the output, so f is equal to c times the e dt is equal to the q dt. Well, the q dt is the volume flow rate, is c times the e dt. See? So that is the C element. C element could be represented also in block diagram form, because the block diagram form, all it's doing is representing the constitutive law. And that's what this does. It's R times 1 over C and times 1 over S, we have E sub 4. Then you have the I element or inertia element, which could be linear or non-linear. The devices, the I element stores kinetic energy. This is like the example of a mass on a mechanical system. So in here, you have a, just like on the C element, you have two possibilities: to write it in the integral form or to write it in the derivative form. The preferred method is always to write in the integral form, because computers are very good to integrate. Computers are not so hard to differentiate because of numerical instability, or if the slope under a curve goes to close to 90 degrees, then that constitutive law becomes difficult, because differentiating is not in the best interest when those numbers they get close to infinity and you get a memory overflow. So we prefer the integral form. That doesn't mean there's something wrong with the derivative form. It's just easier. But normal systems have integral form. It's only when we do some weird connection that derivative form comes up. So that's the constitutive relationship in here. As you can see, one for the integral form and one for the derivative form. We can represent it in block diagram form, and that is 1 over L times 1 over S equals F. This is basically translating this equation. Yeah. Okay, that's the element. Now in here, let's take a look at the source elements, because the source elements, either they are effort source or flow source. In the case of a voltage, that's an effort source because its voltage is an effort variable. In this case of the motorcycle or vehicle going over a bumpy road, this is an interesting question that I always pose to students. Is the ground providing a velocity input or it is a force input? What do you think? Let's say you go in a car and you go through some bumps, you feel them, but you on a motorcycle would be even much more obvious. So the question is the ground putting a flow input or it is a effort input? Is it a force or it is a just the velocity input? What do you think? Is what? It is the velocity input. Why is that? You say, how come, if I go on a bump, I feel the bump. But think what's going on physically. The tire has to follow the profile of the road, and it's going to go up and down. How's it called? The change of the position as a function of time? So the truth is called velocity, right? So in fact, when you go on the road is providing a velocity input. But you could argue, I feel the force. Yes, this is true. But the force is a reaction to the input. See, that's the difference. There's no force input, but there is a velocity input. So what happens is if you enter something with the velocity, it has to go through the dynamics of the system to get a response. So there's those two possibilities. And to illustrate that, we put the SE that you see on the over here, and you put an SF that's next to it. Okay. So this has one set of constitutive laws, and the other one has the other one. Then we have the two sources. These are simple. Either you have the E is obviously source of effort. The I is or F is, SF is source of flow. Now we are left with just two other elements. The one element is the transformer element, and the other one is called the gyrator element. Well, in the transformer element, you could see on the left-hand side, there is this bar that has two forces on the side, and depending on which acts when, the system will move. The one on the right-hand side is another good example of a transformer, because what's happening on this side, the amount of energy is released over here. So if this pushes, then creates a pressure. The opposite is true if voltage here is, if it has an input in here, it will have to have the same type on the other side, because that's what's happening here. It's like the force is proportional to the current. Okay? So again, the constitutive laws are directly related the way the elements are entered. So if you have this, it's worth taking a little patience reading this. If you have this in here, let's see if we can write something in here. If you have it this way, and it cannot be like this, huh? With the transformer, it has to be this way. Okay, this says that the effort 1 multiplied by m times E2. So this E1 is this one times m. Produce this, see? E1 is m times E sub 2. But if you go F1 times m equals to F2, is F1 times F equals F2. Yeah, it's equal to, you could write it like this, F1 times m. Okay, so that's the transformer constitutive relationship. This is how you represent it in a block diagram, because transformer has two equations, one for the effort, one for the flow. And you could represent it like this: E times something equals E4. F4 times something equals F5.
Professor?
Yeah.
So that element can only do one or the other. Either transforms an effort or it transforms a flow, but not one into another.
Yeah. See, let me show you what the scenarios would be if I do that. Yeah, here. So let's take a look here. So we can write in here. You see, what happens here is that, let's see, custom pen. Yeah, we could just do it with a blue pen. You have, in here you have this F4 times this transformer, it gives A5, E5. Okay, so you could write, you could have TF like this, or you could have TF like this. See, you can only have those two.
So you can never have
There can never have something like this. Let me just see if I can. You cannot have something like this. This kind. That's
so
not
another
possible.
element
It's not possible. Another element has that. All right, which is the generator. Okay. Any questions about this one? No. Okay. Let's go on. Let's go on.
Um,
Okay.
what about, for example, with the normal electrical transformer where it kind of affects both the voltage and the current that goes through there?
On an electrical transformer, you have a voltage that gets transformed into another voltage. You don't have a voltage into a current
Yeah.
because that's called a motor. So a motor is basically a type of transformer that has the variables crossed. That's what this is. See here on the right hand side.
So is the change in the current is like the power must equal, does the current kind of come out of the change in the voltage whenever you work with the equations?
Well, yeah. I mean, you see the two equations in there. It says E is equal to R times omega, right? That means voltage equals to the motor constant times the angular velocity. And the other one, the other equation says that the current times the motor constant equals to the torque. In fact, that's how you buy these motors. If you go on a catalog or you go to the hardware store, you have to tell the motor constant because depending on that is how powerful the motor is. But always in the motor relates the voltage to the angular velocity, not the voltage to the current. That's what I'm trying to drive that point across. Okay. And then we have this possibilities in here. Because this is a cross transformer, you could see the one on the here. The way you read is this: E1 is an output of GY. How did that happen? On this side comes F2 times R should be E1. See? F2 times R equals E1. Or you could say F1 times R equals E2. That is also here. See, this, let's practice this. If you have this way, it means on this side, it has E1 multiplied by R equals to F2. I put the prime just to make a difference that is not the same. And this is the input side on the side, so this is E2 is the input times R theta equals to F1. I mean, it's R prime times
transform
F2.
it to a flow.
This effort
Mhm.
times this transforms into a flow.
Okay.
That's what this is saying, see the equation. So always the generators as well as the transformers, they have two equations. They are also called two-port elements because it has both sides. Yeah, and it's just due to the nature of this. You remember what I was telling you? The generator being a cross transformer, this is how the block diagram looks like. It's E5 times the transformation equals F4 or E4 times the transformation is equals E5. Okay, this is the same thing, but just written differently. The zero junction is like a T. Think of a T in a part. It maintains the same pressure, right? But the flows are different. That example should illustrate how this works. But this is the zero junction also in an electrical circuit. You could say this E is the equivalent of the parallel connection, but we cannot use that word across the other systems. So it's strictly to electrical systems, right? But if that helps you understand what the zero junction is, perfect. See, the constitutive laws of the zero junction is saying that all the efforts are the same, but the flows will sum. In fact, if you have a T in a hydraulic system, water comes in towards the T, some goes one way and some goes the other way. It means whatever came in equals to what got out. So it's totally conservative, but at the junction you have the constant pressure, but the flows will add or subtract. You can have the representation of this with the half arrows in many ways. I'll show you under how those relate to the equations, because these are important. If your system has motors or has generators, you will be faced with this question. How should I write the equations? In this one, it says all the efforts are the same, all the flows will add. Same thing here. Okay. Or this one. Yeah, this is important that try when you're at home, try to go over this and see if you can redo it. I'll help you tremendously. This is how you represent the zero junctions now with all the other bonds. Okay? You could have only one effort that causes the effort to all the junction. So like this, in this case was 1, in this case is 2, and in this case is 3. Okay. You can have now, I put a slide together that reveals all the connections, but also all the equations. Because in the first case, you can see all the efforts the same. The flows add up depending on how those half arrows are instructed, in which direction. Or you can have this one on the right hand side, all the efforts are the same, but the flows will add to 0. Same thing is true with this other two. This is the conclusion of the zero junctions. It's a common effort junction. All the efforts are the same. The sum of all the flows equals 0. Okay, so you can only be one bond that sets the effort to all the others. And then we have this one. Yep, go back here.
Power flow and zero junction charts, the first one.
So in conclusion, we can have the zero junctions with all the efforts being the same, but the summation would have to be on the flow side.